In this video, we're going to be talking about critical numbers. So let's just dive right in. The definition here, a number C in the domain of a function, that's important. This has to be in the domain of your original function. And it's called a critical number if the first derivative is 0 or the first derivative is undefined. And in particular, the first derivative is undefined, but C is in the domain of the function, right? So like you can plug C into the original and get something that makes sense, but when you try to plug C into the derivative, you get something undefined. Okay, so let's just do a quick example where we find some critical numbers. Find the critical numbers for this function. So this is just polynomial, so pretty straightforward. So to find the critical numbers first, you want to take the derivative. So we're just going to use power rule here. First derivative is 3x squared minus 6x minus 9. And then once you find the first derivative, you want to think about where is this undefined and where is it equal to 0. Well, because this is polynomial, it's continuous on the whole real number line. It's not going to be undefined anywhere. So to find the critical numbers in this situation, we're just going to think about the places where it's equal to 0. So we take the first derivative, we set it equal to 0, and now we're going to solve. So for example, we can pull out a 3, x squared minus 2x minus 3, and then we can factor this. So this factors into minus 3 plus 1. So this tells me that x equals 3 and x equals negative 1. Both of these are values that make the first derivative 0. And again, because this is polynomial, both of these are in the domain of the original, right? So that means that these are both critical numbers. Okay, well, why do we care about critical numbers and why are they so-called critical to a function? Well, that's going to lead us into a couple of theorems. The first is that critical numbers have to do with maximums and minimums, specifically local maximums and minimums, which we discussed in a previous video. So if f of c, if you have a y value that's a local max or a local min, then maxes and mins only occur at critical numbers. Okay, so that's good to know if you're interested in finding maximums and minimums. Basically, if you want the local ones at least, all you have to do is consider the critical numbers. So that's nice. And the next theorem says that if your function is continuous on a closed interval, so remember, if your function, the extreme value theorem says that if your function is continuous on a closed interval, then it has an absolute max and an absolute min, meaning there's some largest y value and some smallest y value. So if you look at that y value, in this case we're calling it f of c, that's the absolute max or the absolute min, then the location where that happens, right, the x value that goes with that absolute max or min is either a critical number or one of the endpoints, right? So c is actually a or b. So essentially what this says is, or these two theorems are saying, is that local minimums and maximums essentially only happen at critical numbers, and this one says that absolute minimums and maximums happen at critical numbers, and that's the sort of like naturally occurring maximums and minimums, but they can also happen at the endpoints where you're sort of like chopping a function off. So let's just see what this looks like in a graph. So for example, let's say I'm working this one, and I want to find the absolute max and the absolute min. And I'm going to be thinking about it on the closed interval from a to b. So if I look here, right, like this would be a local maximum, but it's not the absolute maximum, right, because all these y values are higher than this one. This would be a local minimum, right? This is a place where the derivative is equal to 0, right? Horizontal tangent lines are derivative equal to 0. So these would both be critical numbers, say x1 and x2. Right, because they are places where the derivative is equal to 0. So my potential places for maxes and mins are, let me get a different color here. My potential places for maxes and mins are here, 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 and here. That's essentially what the theorem above says, is that your absolute max and absolute min happen either at critical numbers or at the endpoints. So as we can sort of see here, we've got sort of one of each. The minimum number is going to be 2, and that occurs at a critical number. And the absolute maximum is going to sort of happen at this artificial one, looks like probably 6. And I'm calling it artificial because if you look at the function as a whole, that's not really this is not a special place on that function, right? This is just part of a continuous curve as it's sort of just climbing and climbing and climbing. So this is why I'm calling it artificial, because this is only a maximum on this interval because we chopped the function off. This one is a sort of much more natural minimum. It's like a natural dip in the curve, right? So it's this local minimum, and it happens to be the absolute minimum on this interval. But this is what I would call a naturally occurring maximum or a minimum. Those are the ones that happen at the local places. And the sort of artificial absolute maxes and mins are what I would call when you chop the function off, right? Again, this one doesn't have special significance except on this interval. So that's what the theorem above is saying. Let me go back to my black pen. So this is what it looks like in a graph, but let's just do a problem where we find the extreme values algebraically, because there are a couple of things you have to keep in mind here. So we'll work through this and talk about them. So first of all, when you see the language extreme values, like extreme value theorem, that's talking about absolute maxes and mins. So when it says find the extreme values, that's asking you to find the absolute maximum and the absolute minimum. Also, just remember that maxes and mins are y values. The x values are where maximums and minimums occur, but if you want the absolute maximum, that is a y value, right? That's a sort of vertical movement. Or not movement, but it's a sort of vertical measure, a y value. So if I want the extreme values, the theorem above, this one, tells me that the extreme values happen at critical numbers or endpoints. So essentially what I'm going to do is first find the critical numbers. So maybe I'll write step 1. Find the critical numbers. And so remember, critical numbers are where the first derivative is equal to 0 or undefined. So of course I need to find the first derivative. And again, this is just polynomial. So this is 3x squared minus 12. Again, polynomial is not going to have any places where it's undefined. You can get things that are undefined. Don't make the mistake of thinking they never happen. I'm not doing an example like that in this video, but if you have, for example, an x to the 1/3 power, you could get a critical number where the first derivative was undefined. So you might play around with that and see what I mean specifically with the function x to the 1/3 power. But now back to this one. We know that this one is not going to be undefined, so we're just going to set it equal to 0 and solve, and that's going to be where we get our critical numbers. So in this case, 3x squared equals 12, x squared equals 4, x equals plus or minus 2. So I get two critical numbers, right? Positive and negative 2. And then if I want the extreme values, step 2 is going to be to plug in your critical numbers and your endpoints and see which ones are the biggest and smallest. So plug in critical numbers and ends. And there's a potential pitfall here, which I'll come back to in just a second. So what were our endpoints? -1 and 3. So we take x and f of x, our original function, and we're going to plug in our critical numbers, positive and negative 2, and also our endpoints, which were -1, 2, 3. And if we plug these into the original function was x cubed minus 12x plus 1. So x cubed is 8. Here it will be -8. So x cubed minus 12x, so minus 24 plus 1. X cubed minus 12x, so this is going to be plus 24 plus 1. So these two are going to give me, looks like -16, -15, and then positive 16, positive 17. And then when I plug in -1, I'll get -1 plus 12 plus 1. So 12, when I plug in 3, I'll get 27 minus 36 plus 1. So looks like -9 plus 1, so -8. So then I would say my max and my min are the largest and smallest values. Okay, so in this case, the max would be 17 and the min would be -15. Except that's not right. Okay, so there's a problem with this, and if you've already recognized it, great. If you haven't recognized the problem, you may want to pause it, the video, and think about it for a second. Okay, so let's go back and see what the problem is here, and this is something you have to watch out for, is that we are only interested in the maximum and minimum on this interval, right? On the interval from -1 to 3. So really, when I got these as my critical numbers, it's true that +2 and -2 are both critical numbers for this function, but are they both relevant for this interval? No, right? -2 is not in the interval in question, which means I do not care about what the y value is for -2. So similarly, when I come down here, I shouldn't have had this line in my calculation, which means that the actual max is not really 17, it's 12. Okay, so in general, this is the process for finding the extreme values, the absolute max or the min. First, you find your critical numbers. Then, after you find your critical numbers, I strongly recommend you compare your critical numbers with the interval in question, right? Throw away any that are not in the interval in question. Like in this case, the -2 should have gotten chucked out. And then after you get your critical numbers, you plug in the endpoints, you plug in the critical numbers, and you're plugging them into the original, not the derivative, but the original function, and you're going to see which one's the biggest and which one's the smallest, right? That's what maximum and minimum mean. So the main takeaway from this video is to talk about what a critical number is. It's something that's in the domain of the original function, but makes the first derivative either 0 or undefined. And the reason that we care about them is because they are very intricately tied to maximums and minimums, right? Local maxes and mins only happen at critical numbers. And if you have absolute maxes and mins, those happen at critical numbers or at endpoints. One other thing to point out here, this theorem, what's called the contrapositive, or not the contrapositive, but the sort of converse of this is not true. Just because you have a critical number doesn't mean it automatically goes with a maximum or a minimum, okay? If you have a max or a min, you know it goes with a critical number. But if you have a critical number, you do not immediately know that it goes with a max or a min. You can have critical numbers that go with neither. For example, the sort of classic example of this is the function x cubed, which looks like this. And in fact, there's a horizontal tangent line right here at 0, even though this is neither a max nor a min. So you can have critical numbers that don't go with either, but if you have a maximum or a minimum, that always goes with a critical number.